Juan Carlos Pichel was going to moderate this doctoral meeting, but he had a personal affair, so he couldn't stay. So whenever you want, Rubén, you can start your doctoral meeting today. Thank you.
We have Tomas here if he wants to moderate something. Tomas?
Yeah. Tomas, it's okay. If he wants to. If he wants to, I can't see him.
Okay, it's fine. I'm going to start. Let's share the screen if Teams wants to. Okay, so everything is fine, I guess. Can you see the slides?
Yep.
Okay, so let's start with this doctoral meeting. I'm Rubén, you all know me, and I'm here to talk about Thanos and the fight for the optimal mapping in NUMA systems. So here is the table of contents for today. First, I will tell you what is a NUMA system and why should we care about this kind of servers. Second, I will talk about the challenge in NUMA systems and mapping threads and memory pages in that kind of servers. Third, I will talk to you about Thanos, our proposal to solve the problem. Fourth, I will show you the results we have collected so far. And finally, I will throw some conclusions and talk about the future work. So let's start telling you what is a NUMA system. So first, we should introduce you what we are used to. And we are all using UMA systems. That means Uniform Memory Access systems. In all your laptops, desktops, even your mobile phones are the UMA systems. And that means that every core has the same latency to access the data in the DRAM memory. In opposition to that, we have NUMA systems that stands for non-uniform memory access. And it's easier to explain what this is with an example. So here we have the topology of CiTIUS 1 here in CiTIUS. And we can see that a NUMA system is a server that is formed by several nodes. In this case, we have 4 nodes. And each node has its own processor and a memory bank. So the key point in NUMA servers is that whenever a thread running in a core, let's put, for example, in node 0, wants to do some operations with memory, data in memory, it's much cheaper in terms of latency to access its own local memory than go for remote data. This thing is supposed to happen in transparent ways for the user. So what we should expect is a huge and powerful system with a lot of cores and a huge amount of memory. But reality is hard, and what we really find is that this is a bunch of processors hardwired, and it's very, very hard to extract performance in this kind of systems. So why should we care about this kind of hard and complicated systems? Well, first reason is very obvious, because we all like having new toys with a huge computational power, where we can throw bigger simulations or make our current simulations even faster. But there is also some interests in companies to increase the performance of this kind of systems. Here we have 2 examples from very well-known companies. The first one is from Riot Games, that you will know for being developers of League of Legends and Valorant. And this is a very interesting article I mentioned here, because they enumerate the challenges they had to face to achieve some performance targets they had to meet in their servers for Valorant. And here we can see that making the best use of the architecture in NUMA systems they've been able to increase the performance and meet that performance target. And the second example is from Netflix. We all know Netflix because we all see the shows and the Squid Game and that kind of things. And we can see in this article that Netflix optimizations to the NUMA scheduler made them almost double their performance in the servers. We can now move on to the challenge of these systems. And well, it's pretty obvious. We want to extract the maximum performance we can from these NUMA systems, but it's kind of tricky because, as we mentioned before, latency for local operations is lower. So we should encourage that local operations, but if we do it too much, we could cause what is known as memory congestion. On the other hand, if we are not encouraging that local operations enough, we suffer from very high penalties because of the remote operation we mentioned before. So as usual, a programmer could take care of that, but let's face it, this is our attitude in this kind of situations. We rather prefer to blame the computer over our own coding abilities. So we can now make an example with a university. So we can imagine we have a university with some faculties that will represent the NUMA nodes of our system. And each faculty has a library that represents the memory bank. And each library has the librarians, which play the roles of memory buses. On the other hand, we have some degrees that play the role of processes, and those degrees have some students that represent the threads. So at the end of the day, what we have, some students that have to do some homework, and to do that homework, they need data in books. Or what is the same, we have some threads that have some calculations to do, and for that calculation, they need data allocated in some memory pages. So let's start with the easiest example here. We have only 2 faculties, and each faculty has only one but promising student. So here we have the computer science faculty and the mathematics faculty. Okay, so let's start with our computer science student. He has some operating system homework to do, so he needs the Tannenbaum book. So he goes to the library and asks our friendly librarian to retrieve the book. And since he's the only student in the faculty, he will retrieve that book nice and easy. And the very same happens for our mathematics student in the maths library with the differential equations book. Okay, we can go to the step forward, and we have 2 students now in each faculty, and you will see that things will start to go a bit messy. So we have 2 students in each faculty, and they will both want to access to the modern operating system book. So they will both go to our friendly librarian and ask for the book. And here we have 3 possible options. We do nothing, so one of the students will remain idle while the other is doing his homework. The second option is to move books across libraries, which is very expensive because the librarian will have to take the book, call the post service in the university. The post service will have to send the book across libraries, and the librarian in the destination faculty will have to do some paperwork, and everything is very complicated and expensive in time. So our third option is the best one. We simply send the students for a walk. So he makes some exercise in the meanwhile, and he can retrieve the book nice and easy in the other faculty. So in this example, we send one of our computer science students to the mathematics faculty so he can grab the book from the maths library. And the very same happens for the student in the math faculty who travels to the computer science faculty and takes the differential equations book from there. Well, with 2 students, things get a bit more complicated. But what happens when we have a lot of students from a lot of faculties looking for a lot of books and doing a lot of homework? Well, our friendly librarian is not friendly anymore, and things is a complete chaos. So summarizing, with what we want to do is to extract maximum performance. And that is something that is kind of easy when we have a low number of threads and memory pages. But the complexity of the tasks increases exponentially with the number of NUMA nodes, the number of cores, the number of processes, threads, memory pages, and so on. So what should we do in that case? Well, we should keep encouraging local operation by migrating threads as much as we can, since it is the cheapest option. But we have to be careful because we might cause some memory congestion that will drop your performance. And in that case, if we fall in the trap, we have to distribute the workload, moving memory pages across the whole system. Now we can introduce you Thanos, our solution to the problem. First, we have to make sure that you all know Thanos, the best villain in the MCU so far. I think we all can agree in that. No? Yeah? Yeah. So in this talk, when we talk about Thanos, we will refer to our solution with a huge and very, very long acronym for that. I had to make some tricks to make the name right. But that tool is particularly interesting because it has two features that outstands from the rest of proposals. The first is it uses the hardware counters to measure performance and profile and make some profile. And second, it works in the user space, which is the pose of what one can expect from this kind of tools. That means that Thanos actually fights the decisions of the operating systems in terms of thread location and memory pages. So what does Thanos do? Well, when things go right, it is supposed to launch your program or set of programs. It should analyze the performance and take some decisions about which threads and memory pages should be moved across the system. On the other hand, when things go wrong, it can wipe out half of your performance. As I mentioned here, reality is often disappointing. How do we use Thanos? Well, it's fairly simple. We just download the code from the repo, we compile it, and we launch the program, specifying our target program as an argument. And hopefully everything goes right and your execution times should improve. We can now explain how Thanos works. And periodically, its 3 stages are executed. First, we do some profiling to collect data. Second, we process that data. And finally, we make some decisions based on the data we collected and processed. So first phase, as I mentioned, is profiling. So we use hardware counters, which are a special kind of registers in CPUs, in modern CPUs, that allow us to measure the performance of the system. In particular, we use the number of operations performed by each thread in the system, the number and the latency of the memory operations performed, and with that we can compute the operational intensity, just computed by this equation, and give us a clue of the efficiency in the use of cache memory. After that, we build some performance table, and with the collected information, we can derive the operations per second, which give us the speed of our code, how fast is it executing. We also compute the average latencies, which will be useful to make some decisions later. We can also know which are the preferred nodes for both threads and memory pages. And finally, we compute the performance of each thread following this equation. We move on now to the decision-making process, and we start by the threads. And first, we have to know which threads should be moved to increase the performance. And we pick those threads whose relative performance is lowest. That means the performance is very low compared to the brothers or the rest of the threads in the process. Now that we know which threads should be migrated, we have to decide which is the optimal location. And to do that, we follow a scoring system based on simple heuristics like this one. If there are 3 cores in a given node, that is a good candidate. It is even better if that is a node close to the preferred node, or if it is even the preferred node itself, and that kind of things. For the memory pages, we decide to migrate those pages whose latency is much higher than the average. That give us a clue that things are going wrong with that pages. And we move them based on whether or not the preferred node is busy. We say that a node is busy when the latency of the pages in that node are very, very high compared to what happened in the other nodes. So if the preferred node, we move the pages to the least busy node to balance the workload, since we have some memory congestion happening there in the system. And if it's not, the locality can be improved. So we move the page to their preferred node. And we also perform some prefetch, like similarly to what cache memories do to exploit spatial locality. I can now show you some results we have collected so far. For our test, we used the machine I showed you before, CiTIUS 1, 4 nodes, 20 cores each node, 64 gigabytes of memory in each node. And this is kind of ideal for the task because it shows some high remote latencies. For the experiments, we have designed 3 experiments covering what we think are 3 common use scenarios for the NUMA systems in industry. First, the single benchmark scenario. Second, an interactive system. And finally, a queue of tasks. And for the benchmark, we choose the NAS parallel benchmark, since they are very well known and they are assumed to have some high quality coding standards. So in the single benchmark scenario, it's the fairly common /benchmark. So all the resources in the system are available to the benchmark running in that precise moment. And since we are using the NAS parallel benchmarks, there is very little, if any at all, room for improvement because of the high quality standards I mentioned before. This is good, actually, because we can estimate our effective overhead of our proposal. So here I show you the results, and in this plot, we can see the normalized execution time. So 100% corresponds to the average execution time of the operating system, just the operating system, and each bar shows the execution time of our proposals. So in this blue bar at the beginning, for example, we can see that our thread migration algorithm increases execution time by 4%. So on average, we can conclude from this result that our effective overhead is on 5%. But we can see that in some scenarios, our algorithms improve the execution times. We should remark that this particular benchmark, which is very intensive on memory, that we improve execution times by 32%, which is great and give us some hopes for the following scenarios. Here we have the interactive scenario, which is kind of an anarchy, because users can launch the benchmark whenever they want. And this is a trace we built based on the usage of servers in Tesla. And here we can see that one user sends a benchmark in the time 0. After some seconds, another user sends another program. After an arbitrary amount of time, another user sends another program, and so on. Here, affinity and locality is very important because there are a lot of processes coming in and out of the system. So here we have the results. And if we take a look at our threads algorithm, migration algorithm, we can see that we improve the operating system in most of the cases, in every case, actually. But our memory migration algorithm is not so good. Did you remember when I told you that when things go wrong, we can wipe out half of the performance? Well, here is an example. And nevertheless, when we combine both threads and memory migrations, we can achieve the best possible results, and in some cases we improve execution times by 60%, almost 60%, and 22 on average. Okay. We have finally our queue of tasks scenario, where we have our system working at 100% all the time. So we have a queue of tasks. So once a task concludes, another task come in, and therefore we have always the system working at 100%, as I mentioned. This is the best scenario for us, and we can see that our migration algorithms improve execution times in a significant amount of time. We have on average an improvement of 30%, with peaks of almost 50%, which is great for us. And finally, we have some conclusions here. Okay. One positive we have is that Thanos performs better than the operating system in most cases, those cases related with multitask environments, but we have some improvements to do in single task environments. We have a low overhead, which is positive for us because we have some less ground to recover here. And our thread algorithms are great. They perform really, really well. But our memory pages migration algorithms are not so great. But here we have an excuse, and it's a well-known problem in the research community that Linux procedure for migrating pages is not very efficient and has a huge overhead. So we hope that once that mechanism is improved, our results should improve too. And finally, we can state that our tool's name is really, really cool, which is the best positive for me. And our future work, we have some disagreements here. My advisors and me, according to me, we should move our algorithms to the kernel so we can have more information available that will lead us to better decisions in terms of which threads and which memory pages we should migrate and which are the destinations. And another positive is that we wouldn't have restrictions. We can do whatever we want, so that gives us unlimited power. This is always great. And according to the supervisors, we should develop more and more algorithms so we can publish more and more papers. And that's everything from me. I'm open now to questions. Thank you. Okay.
I want to the first question. I think that is direct. I don't agree with you in the point that Thanos is the best villain in the Marvel.
No.
No, I disagree. But it's not important. It's important point. No, I would like you to clarify the problem we have with the hardware counters. The hardware counters are not free to use, and the information they give is quite limited. So
yeah,
we'll talk about this issue.
Yeah. When we talked about hardware counters, we would make a very simple explanation, but we can get more in depth here. And hardware counters does not really measure the number of operations. It's like kind of an estimation, because every amount of time with given frequency, they sample what happens with the processor. So the information they give us is quite limited, and their accuracy is disappointing, to say the least. I found a lot of trouble there because we cannot trust blindly the information they give us. And of course, they have some overhead. There is some overhead implicit in reading that hardware counters. You have to open some buffers and read it periodically, process the information. It's a bit costs a bit of time to you. So, well, it's hard to use. It's more like a clue that something is happening, that an information you can trust. I don't know if that explanation is good enough.
Consider some only homogeneous systems. CiTIUS one here is an homogeneous system in the sense that all the nodes are the same.
Yeah.
But do you think that changing to a heterogeneous system where some nodes are faster than others can change the algorithm or
Yeah. Well, first we should mention that we stick to the CiTIUS one because we are poor and we cannot afford more systems. But yeah, if we would have some like heterogeneous system, we should introduce some new heuristics in our algorithms to make sure that the most demanding threads goes to the better cores and better processors. Yeah, but that's a really interesting field we want to explore, and we also consider it. But there are some limitations in terms of availability of that kind of systems, and of course, money.
In this, I want to say that we were trying to buy a new machine with a core that is more than 100,000. We don't have only eight now. We don't have enough money. Yes. Other approach to this problem, mostly when because the problem here is when you in supercomputing center, like Cerca, usually works and notices in a batch way. So in each moment there are only one application running in the node. Your solution runs very well in a multi-task, multi-user scenario. Other approaches were for only one application, make a previous profile, analyze the behavior, take traces of the behavior, and then may use some kind of machine learning process to trying and to determine which is the best model and the best placement for trials, so they can start the application in the best situation. What do you think about this solution?
Well, first, a spoiler, I don't like AI, so I don't like machine learning solutions. So that kind of solutions, I do not mean machine learning solutions. I mean, the previous profiling phase is quite a problem because you need that extra time to make that previous phase. We are better in the term that Thanos improves the execution time blindly. I mean, he knows nothing about your code. He does not need any previous information. He just takes the information from the hardware counters and the system information and just migrate the threads, which is immediate, and any researcher can take advantage of. It saves you that previous profiling phase, and it performs, as far as we know, as well as those other proposals. I cannot read chat from here.
With the performance, how will be the performance of the solution when the number of nodes is higher than 4? We need a machine with more than 4 nodes.
Yeah, unfortunately, as I mentioned before, money is quite a limitation for us because test or servers for our testing cost a lot of money. As Tomas mentioned before, it costs more than $100,000. So we could not try what happens when we have more than 4 nodes, but we expect the results to be good. I mean, not as good as with 4 nodes, because that's everything we tried till now. So some adjustment should be done. But yeah, I expect that Thanos will perform at least well, decently well.
I think, in my opinion, that the most important is to know how different is the local access from the remote access.
Yeah.
If you increase the number of nodes, usually the normal situation that it takes much more time with remote memory than a local memory. With only 4 nodes, in fact, we have another machine that is the NUMA 2 that have other connections.
Yeah.
Additional connection, so the access to, because in this system, access to from one corner to the other corner is lower than access in the same row on the same corner. But if you have other connections,
yeah,
the access is much faster.
Yeah, the difference states in the fact that here from node 0 to node 2, we have to do 2 hops, either by node 3 to node 2 or node 1 to node 2. This is very, very expensive in terms of latency. And other systems have an all-to-all connection. So there could be like another cable going through here and another through here, and could save us some time. With 8 nodes, it's expected that remote latencies are even higher, much higher. So we would have to take like 3 jumps, I guess.
Yes, no problem.
And yeah, latency of memory operations in that case would be huge, and performance would be awful if you keep that remote operations going on.
I think that
There is another question. Yeah.
Yes, can you hear me?
Yep.
Okay, I think I have a question, but I'm not sure because I didn't hear the question of Tomás. I only hear the reply, and maybe the reply could be the same. Let's try. You have a solution, if I understood well, to improve the performance because okay, in the hardware you have better access, less latency to local memory, right? To the local memory of each node, you access faster. The memories, I guess, are homogeneous. I mean, they are all with the same characteristics, okay? So you don't have a system with heterogeneous memory characteristics, right?
Yeah, exactly.
Somehow the problem seems similar to the problems that we have in distributed systems with nodes, machines, and disks also. And when we solve problems there, the locality of the data is very important. And to store the data that is related to other pieces of data is important to record them in the same node to avoid movements of data. Okay.
Yeah, exactly.
Is there some? I mean, have you looked at the kind of systems that are used in distributed databases or distributed systems like those MapReduce, etc., and which could be the similarities and the differences between your work and those kind of works?
Yeah, the ground idea is basically the same because you mentioned local operations, whether it's on memory or on disk, are much faster than remote operations. So there is a clear parallelism or similarity there. With the difference, I think that memory can get I mean, you can ask too much of the memory. So in that case, it's better to make some balance of the workload. I don't know if that happens with distributed databases or not. I'm not familiarized with that kind of problem. But yeah, in the terms you mentioned, yeah, there is a clear similarity.
Okay.
I'm noting that we have to check those works, those papers. There is another.
More questions? Well, first of all, thank you very much for your very nice presentation. I have one question related to AI. You developed your algorithm, right?
Yeah.
Do you think some parts of it can be extrapolated to GPU intensive?
Tomás, can I make a spoiler of our other works? Well, while I was studying the master here, I had developed some solutions to share workload among CPU and GPU. But we use a completely different approach. We focus more on bare execution time than any other metrics based on power counters or something. And that's kind of general. And yeah, I don't know how you could extrapolate that to GPUs. Since in GPUs you already have some overhead because of data transfers you cannot avoid, I guess. So once the data is allocated in the GPU, your jurisdiction here and there is almost none, I guess. I mean, once you launch a kernel, I think you have nothing to do with the GPU. Correct me, Alvaro, that you know more GPUs than me. Yeah, I mean, once the GPU is working, I think there is nothing you can do there. I mean, you have to wait for the kernel to finish, and that's everything you can do, right? No, I mean, you can like interrupt the kernel, so you can distribute the workload somehow with another GPU. Yeah, well, there's some research we are doing in terms of sharing the workload between CPU and GPU, but it's in a very preliminary state. It's very soon to say something relevant about it, but that's something I will keep in my mind. I will ask you, what do you want as a potential user? More speed, like that.
Another problem you face with the GPU that you said that hardware context in GPUs sucks.
Yeah, they are paying in some areas I cannot tell. Yeah, the problem with GPUs is that even though they have some hardware counters and you can make some profiling on GPUs, the overload, the overhead there, sorry, is huge. You cannot take runtime decisions based on that because the overhead is massive. This is the big problem we have faced there. I don't know if that answers the question.
Thank you for your presentation. Have you already started
Something we have discussed like 1,000 of times, 1,000,000 of times, something like that. But we never did that step forward because we always have some paper to do and think when, well, after that, never is going to happen. So, yeah.
The kernel is scary.
Yeah, the kernel is quite scary. So I had one slide prepared for the kernel versus user space discussion, if you're interested in. And yeah, the main problem with developing algorithms in kernel space is that it's really easy to make something wrong and blow the system up. So yeah, we stick to the user level algorithms for now. I hope that with a new student, I can like make some kind of torture, like migrating that to the kernel space. So
Yeah, you're going to find new students.
yeah, this is quite a limitation. Hakuna Matata. Yeah. Okay. Spoiler, I don't like Windows. No one of us like Windows. So I think there is a Windows Server Edition that kind of works with NUMA system. I don't know if it works or it doesn't. Nobody cares. Not even Windows cares, I guess. But no, that's not in our path, our future plans, because a lot of things in our code is Linux based. Like we gather some more information, for example, from the proc folder, that it does not exist in Windows, and most of the functions we need to call to retrieve information from hardware counters are only available on Linux. So the question if we can do that in Windows is, I don't think so. I don't think so, and we don't want to. Yeah, any more questions from people in conference?
So only one last comment is if you pay this guy for the use of the image, the presentation.
No, maybe I can invite him a coffee, but he has to earn it. I can give him like a little trophy printed in the 3D printer. Okay, as far as doesn't has the AI words, it's okay for me.
So there are no more questions. We would like to thank Rubén for the nice and funny presentation and a lot of applause, I suppose.
Thank you, everyone. Oh, there's messages. Okay. Esto es todo, amigos. Hala.
Thank you, Rubén.
Thank you.